We'll be using the exact same hardware that we used in all of the WEG CFW 100 and 300 PID videos, so if you've seen any of those videos, this is going to look real familiar with just a couple changes. We have a single-phase 220-volt input, 1 horsepower WEG CFW 500 drive controlling this jet pump motor. The motor is connected to a swimming pool pump that pulls water from a reservoir and sends it up to these nozzles, which we can turn on and off. The water then drains back to the reservoir. The pressure is monitored using this 15 psi sensor, which sends a 0 to 10 volt signal back to the drive. We're using an external switch to control run stop and another switch to switch between PID's automatic and manual modes. Finally, we'll be using the optional alphanumeric remote keypad to operate monitor PID because it makes everything easier to see. This is the wiring diagram. You can download a copy of that and these other diagrams at the links in the description below the video. Notice that I'm using the drive's built-in 24-volt supply to power both the remote HMI and the sensor. I love that I don't have to buy and find space for a separate power supply. Just be careful you don't exceed the 150 milliamp limit of the 24-volt supply. These each draw less than 20 milliamps, so we're in great shape. The other thing to notice is that I'm using a NEMA 4X drive with a built-in disconnect. Again, another thing I don't have to buy, mount, wire, and make sure it meets the NEMA 4X spec. That's awesome. I've included the Automation Direct part numbers for all the components used, including the selector switches and the sensor's quick disconnect cable. I'm using the option module that comes pre-installed in the drive. If you order it separately, it goes by this part number. If you're using a different option module, well, these pin numbers may be different. Here it is. Again, this NEMA 4X drive with the built-in disconnect is controlling this motor and pump, which pulls water in from the reservoir, which you can't see here, and sends it up to the nozzles, which we can turn on and shut off using these valves. The water drains out the back of the tank into the reservoir. This sensor sends the pressure reading back to the drive using a 0 to 10 volt signal. The sensor is mounted at the bottom of a stanchion pipe to minimize noise. You can learn about that in this video. Finally, we're using the optional alphanumeric HMI display to monitor and control the process and these selector switches to control run stop and the PID auto manual modes. Let's zoom in on the HMI and switches and make everything easier to see and leave space for notes. The drive has been reset to factory default, and I already entered the basic motor parameters and configured the remote HMI. These videos show you how to do both of those, so I won't take the time to explain that here. If I hit run and speed the motor up to say 40 Hertz, sure enough, the water shoots out any nozzle that I open a valve for. Of course, each time I open a valve, the system pressure is going to drop a little. How much? Well, let's use this line of the display to monitor the pressure sensor that's coming in on analog input 1. Let's go to parameter 206, which controls the second line of the display, and tell it to monitor parameter 18, which is the analog input 1 value in percent of full scale. Escape back to the top level, and now we can see the actual system pressure in 0 to 100% right here on the display. Perfect. Now for these videos, let's assume we want to maintain a system pressure of 6 psi. 6 psi is 40% of the sensor's 15 psi, so with one valve open, I'll adjust the motor speed until we get to 40%, which is 6 psi on this sensor. Open another valve, and we see the pressure drop. Raise the motor speed to get back to the 40%, or 6 psi. Open another valve, pressure drops again. Raise the motor speed to get back to 6 psi. Open the last valve, pressure drops. Raise the motor speed again to get back to 6 psi. And if we close the valves, we need to reduce the motor speed to get back to 6 psi. So we just did manually what we want the PID to do for us automatically, right? Every time the pressure changes, we want PID to automatically adjust the motor speed to keep the system pressure at 6 psi. It's really important to notice that our system is capable of maintaining 6 psi regardless of how many valves are open. If we can't manually get the system to maintain 6 psi, then PID won't be able to do it either. PID isn't magic. It can't make your system do something it isn't designed to do. Ours is, so we're good to go. The other thing to notice is that there's plenty of motor speed left over between here and 60 Hertz. I call that headroom. That's important. PID needs that extra motor speed to make fast changes. Kind of like when you step on the accelerator in your car to get on the highway. You mash the gas pedal like you want to go 120 miles per hour, but then when you get close to 60, you back off. PID does the same thing. It needs as much extra headroom as you can give it so it can accelerate quickly to give you a quick response. Finally, we need to know one more thing. What motor speeds give us 0 and 100% of our sensor's range, which is 0 to 15 psi for our demo. So I'll lower the motor speed until I get close to 0 psi, and note that. Then I'll raise the motor speed to the sensor's top end, and record that. But that was for one valve. I'll repeat that for 2 valves, note the speed, 3 valves, note that speed, and 4 valves, and note that speed. If we plot that out, it looks like this. The average is somewhere in here. This line is what PID uses to make all of its decisions. So it's really important that you know what these min and max speeds are. Now we used an average here. If you want the system to be more accurate when lots of valves are open, well, you might want to move the line up here somewhere. If you want the system to be optimized for fewer valves, well, you might want to move the line down here somewhere. Regardless, it's these two numbers over here that tell PID how to react. So make sure you know what those are. Now, if you can't run your system all the way to 0 or 100% of your sensor's range, then get some intermediate numbers and extrapolate. That'll get you close enough. Well, great. We now know that our system can do 6 psi regardless of how many valves are open. We know that our system has plenty of extra motor speed headroom, and we know the min and max motor speeds to get the full range of our sensor. We're now ready to implement PID. Join me in part 2, where I'll show you how to simplify what can be a daunting task, keeping track of all of those PID-related parameters. Using that method, we'll have PID automatically maintaining the system pressure for us in no time. Click here to learn more about the WEG CFW500 drive. Click here to learn about Automation Direct's free award-winning support options, and click here to subscribe to our YouTube channel to be notified when we publish more videos like this one.